What if your biological age is older or younger than your actual age? Scientists are now using tools like epigenetic clocks, blood biomarkers, and fitness tests to better understand how our bodies age. While supplements like NMN, AKG, and Fisetin are gaining attention, current research has not confirmed that they slow aging in healthy adults. Experts say the real foundation of longevity is much simpler: strength training, nutritious food, quality sleep, stress management, and regular exercise. Supplements and advanced testing may support a personalized health plan, but they should never replace healthy lifestyle habits or professional medical advice. The future of longevity starts with the choices you make every day.
N=1 protocol involves tracking over 100 biomarkers every month. He uses whole-body MRIs, epigenetic tests, and constant physiological monitoring to quantify every aspect of his physical state. But the massive volume of collected data obscures a deeper question. What do these systemic metrics actually represent at the cellular level? Medical history is filled with drugs that successfully corrected a number on a page without actually reducing patient mortality. In clinical research, this is known as the surrogate endpoint problem. Lowering a statistical biomarker, like an epigenetic age, by 5 years does not automatically guarantee cellular rejuvenation or add 5 years of actual health span. To extend human health span, we must separate probability-based systemic measurements from the outcome proximal cellular mechanics that dictate aging, like mitochondrial bioenergetics. Confusing the measurement with the mechanism is a critical flaw in modern longevity interventions. It treats the map instead of the territory. Think of the human genome as a cookbook. Biological age is tracked via DNA methylation, where chemical tags attach to the DNA strand, dictating which genes are read or silenced. But an epigenetic clock is not a unified science. Researchers rely on distinct algorithms trained on different datasets. Compare a single sample across 3 popular models. The Horvath clock calculates age across different tissues. PhenoAge indexes clinical health markers, and GrimAge tracks plasma proteins predicting mortality. They will yield wildly different biological ages for the exact same sample. This lack of cross-lab standardization creates a severe clinical limitation, yielding non-reproducible results across different testing facilities. When a subject alters diet, changes their sleep, adds heavy exercise, and takes daily supplements, identifying which intervention actually caused a metric to shift is scientifically impossible. There is also the Hawthorne effect. The intense discipline required for extreme self-monitoring changes a person's behavior, and that behavioral shift cannot be cleanly separated from the physiological effects of the interventions themselves. Ultimately, a DNA methylation age is an outcome distal metric. It provides a statistical probability of disease risk, but it is not a mechanical biological lever you can pull. We have to contrast these probabilistic clocks with outcome proximal functional markers, specifically VO2 max and grip strength. A functional grip strength test directly measures what the body can do. A 5-kilogram decrease in grip strength is associated with a 16% increased risk of all-cause mortality, proving to be a highly robust predictor of lifespan. Epigenetic clocks provide a highly detailed, probabilistic map of age-related disease risk. They cannot, however, tell us the functional capacity of the body's physical machinery. When we look past the systemic blood panels and examine the cytoplasm, we find clusters of warped, damaged mitochondria, organelles that fail to maintain bioenergetic homeostasis. As these dysfunctional mitochondria accumulate, they propagate widespread cellular damage by leaking reactive oxygen species, driving tissue aging and systemic inflammation. This diagram illustrates mitophagy, the cellular clearance mechanism that recycles failing mitochondria. The pathway initiates with pink-1 proteins accumulating on the outer membrane of a damaged mitochondrion, acting as a distress signal. These tags then recruit the Parkin complex, a larger structure that binds directly to the damaged site. Finally, an LC3 autophagosome completely engulfs the tagged structure, digesting the broken mitochondrion into reusable particles. This essential cellular clearance process naturally declines as we age, leading to a toxic accumulation of cellular debris. The process is heavily regulated by biochemical signaling. mTOR signaling generally inhibits this autophagic clearance, while AMPK signaling actively promotes it. Restoring this specific bioenergetic clearance mechanism is a mandatory prerequisite for neuroprotection that targets the source of pathology, operating entirely independent of distal blood tests. Urolithin A acts as a potent mitochondria enhancer and a direct inhibitor of DYRK1A kinase, a regulator involved in the phosphorylation of tau. The compound originates from elagitannins, which are natural polyphenols found in foods like walnuts and pomegranates. Preclinical evidence demonstrates urolithin A's efficacy in advanced Alzheimer's disease mouse models, specifically the 3XTG and APP-PS1 lines. In these models, early intervention with urolithin A successfully mitigated both amyloid beta deposition and tau pathology. The compound physically reduces IL-1 beta-mediated neuroinflammation and preserves critical synaptic plasticity. But here is the clinical reality. Humans cannot simply drink pomegranate juice or take standard extracts to reliably achieve these neuroprotective bioenergetic effects. This logic tree maps out the bioavailability bottleneck. When ellagic tannins enter the human gut and break down into ellagic acid, they face three distinct metabolic pathways, driven by the individual's gut microbiome. We divide these into urolithin metabotypes. The UMA metabotype correctly produces urolithin A. The UMB metabotype produces less effective variants, and UMO microbiomes are non-producers. Age is a major determinant of these metabotypes. As we get older, the less effective UMB profile increases, a shift that directly correlates with worse cardiovascular biomarkers. This extreme metabolic variability is exactly why standardized pomegranate extract trials in humans frequently fail to show consistent results. Because bioavailability is strictly bottlenecked by individualized gut microbiomes, applying a generalized, rigid nutritional protocol across a wide population is scientifically inadequate. This split screen illustrates the relationship between systemic clinical tracking and mechanical cellular induction. Intense, single-subject experiments successfully raise awareness for preventive diagnostics, but raw data without medical interpretation remains noise. Epigenetic clocks and 100-point blood panels provide an incredibly detailed but purely probabilistic map of your age-related risk. Validated physical interventions, like caloric restriction and exercise, combined with targeted bioenergetic compounds like urolithin A, are the actual vehicles moving us across that territory. Measurable longevity interventions rely on restoring bioenergetic homeostasis at the microscopic level. Improving systemic biomarkers should be the natural consequence of cellular repair. It is never the primary goal of the intervention. A scientifically sound longevity protocol demands verifiable cellular mechanics paired with expert clinical navigation. That is the only way to translate raw biochemical data into actual functional human health span.